All right, we're going to walk through some examples of how we kind of use and interpret these binomial coefficients and Pascal's triangle. So in example 1, it says let C equal the set with the values 1 through 9, and how many subsets of C have cardinality 6. Okay, so just start with example 1 here. So first thing we need to note is that the cardinality of C is equal to 9. There are, of course, 9 elements, 1 through 9, and this is going to be our value of n. Okay, so now remember, one of the things that the binomial coefficient, which is n choose k, tells us is the number of subsets of size k. So this is size of subsets, and this is the cardinality of the set. Okay, so the number of subsets of cardinality 6 would be exactly this value. So our n is our 9, and since we want subsets with size 6, 6 is our value of k. All right, so how do we go about finding that value? So we're going to use Pascal's triangle. And the 9 basically tells us what row we're going to be in. And then the 6 tells us how many to go over in that row. But we do have to be a little careful because in the triangle, both n and k start at 0. So basically the n values go this way and the k values go this way, if that makes sense. All right, so remember, up here is n equals 0. Then we have n equals 1, n equals 2, etc. So here's 3, 4, 5, 6, 7, 8. We're looking for n equals 9. And notice also kind of a shortcut way to find that is if you look at the second number in the row, that tells you what the value of n is. So this 9 right here is telling us n equals 9. All right, so we want to be in this row right here, and we're looking for a k value of 6. So k starts at 0, again, like n. So this is, oops. This one is k equals 0. This 9 is when k equals 1, etc. So this is k equals 2, 3, 4, 5, 6. And we end up right here at 84. So that tells us up here that 9 choose 6 is equal to 84. So we conclude that C has 84 subsets with cardinality 6. All right, awesome. So that's our answer to number 1. All right, I'm going to erase all this so I can have space to do number 2. So number 2 is talking about an expansion of a polynomial. This time we have the polynomial x plus 2 raised to the 7th power. Okay, and all right, let's get the pencil back here. We'll do this one in green. All right, so our polynomial is x plus 2 to the 7th power, and we want to know what is the coefficient of x to the 5th. Okay, so this one looks a little bit different because in the notes we had talked about the expansion of x plus y, but really you can pretend this 2 is a y if you want. And remember, x plus 2 to the 7th is x plus 2 multiplied by itself. I'm not going to write these all out, but this would be 7 times. Okay, so to get to an x to the 5th, we would need to choose exactly 5 of these factors to contribute an x term. Okay, well, if 5 of them are contributing an x term, that means the other 2 are contributing a 2, right? Because each of these terms has to either give an x or a 2. So there's 2 left over, right? Because 7 minus 5 is 2. So that means we're going to have x to the 5th times 2 squared. All right, if that's throwing you off, you can think about it as x to the 5th times y squared. And in this case, our y is just equal to 2. All right, now we know there's going to be some coefficient here as well. So we'll come back and find that coefficient in just a second. Whoops, that's not a 2, that's a 5 up in the exponent there. And then, of course, 2 squared is 4. So I'm going to write that as x to the 5th times 4. All right. So how are we using Pascal's triangle here? So since this polynomial is to the 7th power, that's our value of n. All right. And we want to know how many x to the 5th terms are there. So that's telling us our k value. All right. So in other words, we're trying to use Pascal's triangle to find 7 choose k. Oops. All right, so we're going down, and again, let's use that little trick where instead of counting to n equals 7, we find the row where the second number in is a 7. That's just kind of an easier way to do it. And then remember that the k's are going up from 0, and we're looking for k equals 5. So k equals 0, 1, 2, 3, 4, 5, puts us right here at 21, all right? So that means there's a 21 hanging out right here. Whoops. There we go, in front of this x to the 5th, okay? But we want to know what is the coefficient of x to the 5th. So since we have 21 times x to the 5th times 4, that would really be 21 times 4 times x to the 5th, and 21 times 4 is 84, x to the 5th. So our answer here to what is the coefficient of x to the 5th in the expansion of x plus 2 to the 7th is also 84. All right, and just so you know, just happens to be a coincidence that I chose 2 examples, which both have an answer of 84. But hopefully that gives you a better idea of how we are using